Good morning, everyone. My name is Tanish, a final year student in Computer Network and Security program. Today, I'm proud to present my project, the Secure Offline Biometric Encrypted Notepad application. This project was developed under the supervision of Dr. Muhammad Zafran, focusing on the intersection of mobile security and modern cryptography. Today, my presentation will follow this outline. We'll start with problem background and objectives, look at how the system compared to existing ones, dive into the design and tech stack, and conclude with the implementation, results, and future recommendations. The Why do we need another Notepad app? Currently, mainstream applications like Google Keep or Evernote are built for productivity and cloud convenience. However, this creates a major security gap. Cloud dependency exposes sensitive nodes to server breaches and unauthorized hosting provider access. Furthermore, most apps lack granular security. They don't offer node level encryption or app level authentication. If someone grabs your unlocked phone, your most confidential data is immediately visible. To solve this, I set three main objectives: to build a note-taking application that utilizes AES-256 encryption and biometric authentication with a local-only storage philosophy, to integrate defensive features such as emergency wipe, tamper detection, and encrypted backups, to enable secure offline sharing via QR codes and validate the entire system through structured security testing. The scope of his project is strictly defined by four pillars: high level AES 256 encryption, biometric authentication, a fully offline operation to eliminate cloud risk, and rigorous testing and evaluation phase to ensure the app is production ready for high security users. If you look at the current market, Google Keep offers no encryption, Evernote is only partial, and while Apple Notes is better, it is still tied to the iCloud ecosystem. My proposed system, the only one that combines AES-256 encryption with a strictly no cloud policy and auto-wipe feature triggers upon a detected breach. I utilize the waterfall model for development to ensure clear requirement specification before moving into design. The tech stack includes Java within Android Studio, SQLite for local data management, and Android keystroke for managing cryptographic keys for security. I implemented the AES-256 in GCM mode and SHA-256 for credential hashing. The system was developed and tested on an Intel Core i5 workstation and deployed on a physical Android 9.0 device equipped with a biometric sensor to ensure the hardware block-backed security features work in real-world environment. The application follows the model view controller architecture. This allowed me to separate the data logic from the user interface. We have five core subsystems: authentication, node management, backup and restore, QR sharing, and emergency security. This modular approach ensures high cohesion and loose coupling, making the app easier to maintain and more secure against side channel attack. Our database consists of five entities. The user table handles credential and security thresholds. The node table stores the encrypted content. Importantly, I've included login attempt table. This is engine behind our brute force protection and emergency wipe logic. If the attempts in this table exceeded the user-defined threshold, the system initiates a self-destruct sequence of the local data. Let's look at the cryptography. We are using AES-256 GCM. GCM is vital here because it provides both confidentiality and authenticity. If an attacker tries to modify the encrypted file, the decryption will fail. I use the hardware-backed Android keystroke, meaning the encryption keys never leave the secure execution environment of the device. Additionally, a fresh IV or initializing vector is generated for every single node to ensure the identical nodes result in different ciphertexts. Security is layered. We have SHA-256 hashing for pins, a configured brute force lockout, and per node re-verification. If you are logged into the app, you can choose to lock the specific nodes that require second biometric check to open. Finally, the emergency wipe feature ensures that if the device falls into the wrong hands, the data is permanently erased after X attempts. Here you can see the UI. In the settings, user can set their max fail attempt on the lock screen. If the limit reached a 30-second, if the limit is reached, a 30-second cooldown enforced. Slide 15 shows the main dashboard after an emergency wipe. All nodes are gone. In the editor, there is a real-time security strength bar that warns us if the node content is too predictable or lacks of complexity. Testing was rigorous. Black box testing covered 10 functional cases, including pin setup and CRUD operations. All 10 were passed. White box testing verified there were no memory leaks in the encryption loops and that every logical branch in the lockout timer was covered. I conducted a UAT with 5 distinct profiles, ranging from journalists handling confidential sources to an IT professional. The task completion rate was 100%. The feedback was overwhelmingly positive, and especially regarding the security strength bar, through some users requested even more advanced features like inactivity auto locks. In conclusion, all three project objectives were successfully met. We have created a fully offline high security notepad that treats data privacy as a right and not a feature. For future work, I recommend integration the modern Android biometric prop API for even smoother authentication, finalizing the QR-based peer-to-peer sharing implementation, implementing inactivity-based autolock to protect nodes if the user leaves their phone unattended. Thank you for your time.